Okay, so we have developed a formula for differentiation. And that is if we have some function where y is a function of x, then the derivative of y with respect to x is equal to that function evaluated at x plus some infinitesimal change in x minus f evaluated at x divided by the infinitesimal change in x. So let's take some function where y is equal to, well, that function f of x, which is just a straight line equation. We're going to start with that, mx plus c. So what is dy by dx? Well, first we go and find out what dy is. And we see on the right-hand side that that is f of x plus dx minus f of x. So that is this equation evaluated at where x is equal to x plus dx. So we get m times x plus dx in brackets plus c. And then we have to subtract that equation evaluated at x. So we have minus mx minus c. We expand these brackets out, so we have mx plus m dx plus c minus mx minus c. And we notice that these mx's cancel out and these c's cancel out. So what we are left with is m dx, and that is dy. However, we want to find dy by dx. So we just divide that by dx, and we see that dx also cancels out. So we see that this just finds the gradient of a straight line equation. But next we apply it to equations that do not describe straight lines. So let's take, for example, y, which is a function of x, and that is equal to a times x squared. For a bit of difficulty, we'll just add bx plus c. Okay, so we've got a nice little equation there. What is dy by dx? Well, we find the top part, which is dy, and that is equal to, well, that function f of x plus dx minus f of x. Now, f of x, we already know, that's ax squared plus bx plus c. What is f of x plus dx? Well, we substitute all the x's in the equation with x plus dx squared plus b times x plus dx plus c. And we subtract ax squared plus bx, messing up the sign there because we're subtracting, minus bx minus c. So let's expand these brackets out. We have ax squared plus 2ax dx plus a dx squared plus bx plus b dx plus c. And then we subtract that second bit, so that's ax squared minus bx minus c. So from the way I've laid it out there, you can already see that these cancel out. And that is dy, but we want to find dy by dx, so we divide by dx. And we see that, well, this dx cancels out, this dx cancels out, and one of these dx's cancels out, so we can do that. And we now apply a bit of trickery, because we have to remember that dx is infinitely small. So it is basically 0. And therefore, we can get rid of this term. And what we are left with is 2ax plus b. But I suppose at this stage it may be worth pointing something out, as you may have spotted a pattern here. We have said that y is equal to ax squared plus bx plus c. And we've said that dy by dx is equal to 2ax plus b. But let's expand our notation a little bit. We have ax squared, so that's a times x to the second power. We have b times x, and that is b times x to the first power. And we can also say that c is c times x to the 0th power, because x raised to the 0th power is equal to 1. But then if we look at the derivative here, we have 2ax, and we can say that that's 2ax to the power of 1. And then we can have bx to the power of 0, because x to the 0 is just 1. And then finally we add 0 times cx to the minus 1. Now this is a bit of a fudge, but it will demonstrate what's happening here. And we also notice that actually in front of that b, we can write a 1. Now I hope that you start seeing the patterns here. When we differentiate a simple polynomial, what we take is that order and we put it in front of the term. And then we reduce the order by 1. And we find for any simple polynomial which takes the form of, well, let's say y is equal to a times x raised to the power of n, some arbitrary power, we find that dy by dx is equal to n multiplied by a multiplied by x raised to the power of n minus 1. And this holds for any polynomial. And from that, I hope that it is also not too much of a leap for you to see that if we have y is equal to ax squared plus bx plus c, that the derivative dy by dx is then also equal to the derivative of ax squared plus derivative with respect to x of x bx plus derivative c with respect to x. And it becomes very clear then that if there's no x component in what you are taking the derivative of with respect to x, that becomes equal to 0. So let's have a look at some explicit examples. Let's say that y is equal to 4x squared plus 2x plus 3. And then we ask, what is the slope at x equals 2? Well, okay, so we take dy by dx, and dy, that is equal to f of x plus dx minus f of x over dx. Now I keep on explicitly writing this expression because it is useful to remember this, because later on as you learn more calculus, then you'll find that there's lots of weird rules like the product rule or the chain rule. And these are useful little shortcuts in which you can use to perform these calculations. However, they are all just shortcuts, and this is the general case that always works, just in case you get stuck. However, this is a very slow method. So dy is equal to, well, 4 times x plus dx squared plus 2 times x plus dx plus 3 minus, well, 4 times x squared minus 2x minus 3. Now we can just cancel these 3's straight away. Okay, and let's expand this out. So that is equal to 4 times x squared plus 8 times x dx plus 4 times dx squared plus 2 times x plus 2 times dx minus 4 squared minus 2x. All right, and we just straight away cancel these ones out and that one. Okay, so let's get the rubber out. And this is dy, but we want to know dy by dx. So we divide that by dx, and we see that this dx cancels out, this dx cancels out, and this one cancels out, and we get a rubber out again. And we've established that this one vanishes to 0 because dx is infinitely small. So we have our equation there. But we wanted to find the gradient at x is equal to 2. So we just plug that in. So that is equal to 8 times 2 plus 2, which is equal to 18. And now let's think about the next exercise. What shall we do? Yes, let's take that equation. Let's get rid of that. All right, so we've already established y and the derivative of y with respect to x. We now want to find when dy by dx is equal to 0. And then this is quite straightforward. We set 8x plus 2 is equal to 0. And then we find out this is the case when 8x is equal to minus 2 or x is equal to minus 2 over 8. Now, why is this useful? If we think about it, we have our equation. And so this is x, this is y, and it roughly follows that pattern. Okay, and this is f of x. What did we say it was? Equals 4x squared plus 2x 3. So why was this exercise useful? So this finds when the gradient is 0. And that is, in this case, the lowest point, where there is no change in y. And this will come in useful in the next section. And that is where we start looking at projectile motion.